We covered marginal analysis earlier in this semester. Now we want to revisit this application of calculus, but looking at it in the context of multivariable functions. For a quick review, when we're given a function, f of x, we can find f prime of x, the first derivative of that function. And one thing that allows us to do is approximate our function value if x is increased by 1 unit. So if x is increased by 1 unit, what will be the impact on our y value or our function value? For a given multivariable function, f of x comma y, we can find f sub x, xy, meaning the first partial derivative with respect to x, and the first partial derivative with respect to y, f sub y. This will allow us to approximate our function value if x is increased by 1 unit. And we investigate that by considering f sub x, the first partial derivative with respect to x. Or we can approximate our function value if y is increased by 1 unit. And we do that by considering f sub y, the first partial derivative with respect to y. Before we get into calculating these, we want to look at just interpreting some results to see how we approach this, given the fact that we're treating one variable as changing and holding the other one as a constant, just like we did when we found partial derivatives manually. So in example 1, we want to assume a given function, capital M of xy, gives the mileage in miles per gallon of a new car as a function of tire pressure x in pounds per square inch and speed y in miles per hour. We want to interpret the following values. So in part A, we have m sub x of 23,44, meaning we found the first partial derivative with respect to x, evaluated it at these given x and y values, and ended up with a result of 0.7139. What these results tell us is that when the tire pressure of a car, which is our x value, is 23 psi, and the speed of the car, which is our y value, is 44 miles per hour, increasing one of the two variables, in this case it's our x variable since that's what we're differentiating with respect to, so we're increasing the x variable, meaning we're increasing the tire pressure, and maintaining a constant speed. If we're differentiating with respect to x, we treat y as a constant, so speed remains constant. That will have the impact of increasing our mileage, and we know that because our resulting function value is something positive, something greater than 0. So when x increases by 1 unit, our function value will increase, specifically by 0.7139 miles per gallon. That is, in this case, if we maintain the same speed and increase our tire pressure, we'll improve mileage for the car, gas mileage for the car. In part B, if we find m sub y, the first partial derivative with respect to y, and evaluate that at 22,56, then what we're saying is when the tire pressure of the car is 22 psi and the speed of the car is 56 miles per hour, increasing the speed, since now we're treating y as the variable that we're differentiating with respect to, so increasing the speed by 1 mile per hour and maintaining a constant tire pressure, will in this case decrease, since the function value of our derivative function is negative. That will decrease mileage by 0.5802 miles per gallon. So that is maintaining our tire pressure, but increasing our speed by 1 mile per hour will decrease total mileage. We want to look at the same thing in example 2, but now we have a function s that gives an ice cream shop's daily sales as a function of temperature x in degrees Fahrenheit and rain y in inches, and we want to interpret these values. If we find in part A s sub x, evaluate at these two values, then what we're saying is daily sales will increase, since our derivative value, the result of that function being evaluated at those points, is positive, at a rate of $251.99 per 1 degree increase in temperature. When the temperature is 88 degrees Fahrenheit and the rainfall is 0.9 inches. In part B, now we have the first partial derivative with respect to y, evaluated a pair of xy values. In this case, this information tells us that daily sales will decrease, since the resulting function value is negative, at a rate of $2,543.73 per 1 inch increase in rainfall, when the temperature is 100 degrees Fahrenheit and rainfall is at 1.14 inches.